Graphite is used in many industries in the form of fine powder. Mills can be used to obtain fine graphite. They mill the graphite mixture as a result of mechanical impact and the abrasive effect of grinding solids on the particles. But such equipment consumes a lot of electricity and requires a long time to process graphite to obtain particles of the required dispersion. And it is very difficult to get the fineness of grinding down to 1 micron or less. Vortex layer devices function on the basis of another approach, which is to use the energy of a rotating electromagnetic field. Ferromagnetic particles move at high speed along complex trajectories and constantly collide, forming a vortex layer. This takes place in the working chamber of the device under the influence of electromagnetic field. At the same time, other physicochemical effects occur. Mechanostriction, ultrasonic oscillations, high local pressures, and in a liquid medium, cavitation also. Due to this intensive mixing, ultrafine grinding and activation of processed substances takes place in the working chamber of the device. GlobeCore conducted a two-stage experiment to evaluate the prospects of vortex layer devices for the production of graphite micro and nanopowders. In the first stage, our goal was to mill graphite in a dispersion medium from an average particle size of hundreds of microns to particles whose sizes are measured in the tens of microns. And in the second stage, the possibility of dry grinding of graphite from an average particle size of several microns to a size of less than 1 micron was checked. First, we prepared 600 grams of graphite, 1.65 liters of distilled water and 500 grams of steel ferromagnetic particles with a length of 15 and a diameter of 1.5 millimeters. All of this was placed in the working chamber of the vortex layer device AVSP-150 and was milled for 10 and 20 minutes. The samples were examined then using a T-scan Vega 3 scanning electron microscope with a measurement limit of 3 nanometers. You can see the image obtained with the microscope on the screen now. According to the results of electron microscopy, it was discovered that the average particle size in the initial sample was 230 microns, after 10 minutes of milling, in the AVSP-150 machine, 38 microns, and after 20 minutes, 14 microns. We used 1.8 kilograms of graphite and 500 grams of steel ferromagnetic particles for dry milling. Milling in the vortex layer of the graphite milling machine AVSP-150 was carried out for 30 and 60 minutes. You can see the granulometric distribution of particles in the initial and milled samples on the screen now. It can be seen from the graph that the distribution has a Gaussian asymmetric character and is shifted towards particles with a size of 14 microns. The maximum for the initial sample is for particles with an average size of 1.56 microns. The maximum for the sample milled for 30 minutes is for particles with an average size of 0.72 microns. And the maximum for the sample milled for 60 minutes is for particles with an average size of 0.64 microns. Thus, the experiment confirmed the perspective of using graphite milling machine AVSP-150 for the production of fine graphite powder, nanographite and graphene derivatives. Fine graphite powder obtained using graphite milling machine AVSP-150 can be used in the production of electrical appliances, batteries, paints, plastics, lubricants, and to obtain the desired shade of cement. Due to its good adhesion to metal surfaces at high temperatures, fine graphite powder can be used in the technological processes of ferrous and non-ferrous metallurgy, as well as in metalworking. Also, graphite milling machine AVSP-150 can be used to mix and evenly disperse small amounts of graphite and graphene and other components. And how do you think, what other substances can be processed using graphite milling machine AVSP-150? For more information about the graphite milling machine AVSP-150, follow the link in the first comment or visit our website, www.globecore.com.